Hello everyone, we are David OSOWIECHI and Gustavo Vargas Hakim from ETS and the Lydia Laboratory in Montreal, Canada. We're going to explain the paper TTTFlow on supervised test-time training with normalizing flow. Deep neural networks are fragile to the problem of domain shift at test time. So test-time adaptation, it trains to adapt a model that has been pre-trained on a source domain to a target unlabeled dataset, also without having access to any of the source samples, which makes it a very complex adaptation scenario. Test-time training has been one of the most popular approaches for test-time adaptation, in which we utilize an auxiliary task that is trained during the source training, and that can also be used at test time for adaptation. In this case, TTT and TTT++ propose different self-supervised tasks, such as rotation prediction and contrastive learning, respectively. In this work, we focus on normalizing flows, which are invertible and differentiable generative models capable of transforming the distribution of a dataset into a tractable distribution, such as the multivariate Gaussian, which allow us to use the change of variable rule to compute the exact likelihood of all the members of the source dataset with terms of the distribution in the latent space. To work with images, we utilize the affine coupling layers from real MVP, such that we can split the inputs into two parts, in which the first part can be used to compute the affine parameters that transform the second part. So the goal of our work is to use a normalizing flows as a shift detector at test time based on the source pre-training.
Normalizing flow will be used as an auxiliary task. As you can see here, we use a Y-shape architecture. So the first step will be to have a pre-trained classification network. And after we will train the normalizing flow on the same data set. Here it will be CIFAR10. Then at test time, we're gonna freeze normalizing flow and classifier and update the feature extractor thanks to this unsupervised task with the negative log likelihood loss. We compare this method with other main method in test-time adaptation and on CIFAR10C dataset, which is composed of 15 corruption. As you can see here, we got a better average compared to the other methods. And also TTTFlow beats the baseline on many corruption except elastic transform and JPEG compressions. We make the same experiment with another feature extractor, which was trained with cross entropy and contrastive learning. It's used by TTT++, and as you can see again, the results are really good compared to the other main methods. Finally, we wanted to visualize what is made by the normalizing flow. So at the upper left corner, you can see that before adaptation, it's really hard for the model to make a good prediction. Then after the adaptation, it creates groups of features which make it easier to make a good prediction for the model. Finally, we also compare with another dataset, which is more natural domain shift. And as you can see with the classical encoder, TTTFlow has an improvement, but which is not really huge compared at before. And this can be explained because the feature from CIFAR10 and CIFAR10-1 are really similar. And with another encoder, TTT++ outperform TTTFlow. But this is true for few iterations after it decreases really fast, whereas TTTFlow is really stable. To conclude, we can say that normalizing flow can be used as domain shift detectors. Thanks for listening. Contact us if you have any question.